The following video is related partially to things I've covered before on lots of subjects, and also video gaming, and kind of mostly as a note to self about how I would do a game like Rust, or actually any survival type game, and whether or not in a survival situation or in a shit hit the fan, the end of the world as we know it, what you would do really to rebuild. Besides reusing things and recycling things and repurposing things, which is really what you would do. In prehistoric times, the 7 metals of antiquity and alchemy, which humans had been able to figure out, name, identify, and find use for, were the following. Melting points and then the element or metal, which are two different things. Gold at 1900 degrees Fahrenheit or more. Silver at 1700 degrees, 1900 degrees Fahrenheit copper, 449 degree Fahrenheit tin, which is, that's something you can do in an oven real easily. 600 degree lead, approximately. I'm not quoting the numbers exactly. Look below in the description or look it up online. Again, that's another element we use. 2800 degree iron, and also room temperature liquid mercury. Many probably an accidental byproduct of various processes. For instance, a lot of these are from campfire temperatures at 700 degrees or lower. These were discoveries from just making a fire and finding out the rocks you used would start sweating, as the term is used these days, or crying tears of metal. And other materials that aren't recognized by people as metals, but they really are metals. Which ones occur naturally in their chemically useful state or mechanically useful state? Gold regularly occurs in nature as a native metal. So gold and a few other elements or just materials that are metals or materials are found, and you can just start working them cold or heating them up somewhat in a fire. 700 degrees. You can get a campfire at 1,000 degrees, by the way, but you get the idea. Silver also could be found that way as well as meteoric iron or sky iron, which is the earliest form of iron that we know of, 400 BC. Copper at 9,000 BC can also be found in raw lumps because the environment underground is hot enough, whether it be from volcanic activity or from mechanical pressure causing it, to cause copper to form lumps that are almost purified. This should be brought up later on in the video here, but there is a specific form of copper ore that you don't have to smelt it, S-M-E-L-T, you just melt it. Because of the way you do it, it ends up smelting it by accident. When people found that some coppers would come out as useful materials and others wouldn't, they started experimenting. Silver, iron, and other metal ores can occur natively, but most are chemical compounds or are bound to something. Compounds are bound, is what we used to say. In a mineral or ore. These contain the useful metallic elements that are bound to other elements as oxides that have oxygen, or a sulfide by sulfur, or carbonates that have carbon, oxygen, and other things like that. It almost always includes carbon and oxygen. These compounds can be decomposed or uncompounded to free up the metal element and whatever it's attached to if the temperature is above or below a certain specific point, usually around the melting point, usually above it. Now, if you're not aware of it, certain compounds of certain metals make the melting point lower than the melting point for the material. Other times it causes them to do very goofy behavior. Now, I'm going to do this as good as I can. Malachite, copper, or other carbonate ores, or galena, lead, or other sulfide ores, must first be put through more than one process. This one will be called the roasting process. In the presence of, let's say, oxygen from air, for instance, these undergo a chemical reaction that causes the oxygen to bond to the ore body, selectively not binding to the metal or selectively binding to the metal, usually to the metal. to remove or burn off the sulfur as sulfur dioxide gas, and also convert them to an oxide that can be more readily reduced to a metal. The idea is that the oxygen will either bind out the metal you want, bind out everything else, bind out exactly what the metal was bonded to, or cause both of them to bind with the oxygen and therefore make it into an oxidized version of the material. In smelting, at a temperature that's almost always above the metallic element's melting point, but sometimes it can be below that for certain stages, depending on the complexity of what you're doing, you can use charcoal as carbon that combusts with the oxygen in the air to produce carbon monoxide, specifically in a reducing atmosphere, as it is called, and that can react with the metallic compounds in the ore to remove an oxygen atom from the metal and form carbon dioxide at that point. This removes and isolates an oxygen and then leaves the raw metallic element to bond with itself, because metals, most of the time, if not always, will readily bond with themselves and begin to pool or trickle or sweat out. This leaves the raw metal also mixed with ore impurities that can become slag with the use of flux, like calcium carbide or calcium oxide or lime, that would pull it up to the top by being less dense, or pull it to the bottom because it's more dense. And you can also do several processes based on each individual ore you start off with. It's not the element you're working with, it's the combination you start off with that determines your processes. Tin and lead are some of the metals with the lowest melting points, and are also elements that can be found to reduce the melting point of other things. Sometimes low melting point elements mixed together will produce a higher melting point for some reason. Let's move on. The others can be done in pottery kilns, blast furnaces, etc. 5,500 BC is when that was done, because pottery was the source for a lot of these. These require temperatures that exceed the melting points in almost all cases. Lead was often a byproduct of the silver smelting process, and steel, let's just get that one out of the way. Let's talk about steel. It's a mixture of iron and carbon in a certain ratio. If it contains too much carbon, it's called pig iron. And to remove the carbon, you blast it with as much as possible purified oxygen that would shock it loose from the mixture of the metal. Next. More resistant to impact damage than wood, bone, or stone equivalents, many products produced by human beings have existed. Bronze happens by combining copper at 5000 BC with tin in the right proportions, and was likely a tin-contaminated copper ore that contained more than one element. You'd be surprised how many elements can be found in one chunk of rock or gravel or whatever. That happened at 4200 BC, later on. Tin is a semi-rare concentrate tin metal ore that was mostly processed primarily at 3500 BC. But again, tin could also be found in ore with copper, and the copper would act as a leaching material to pull out the tin. Now, copper ore is often also contaminated with arsenic naturally. Now, at that point, you realize that if you have this ore and you happen to have it surrounding your fire pit and you get it really, really hot somehow, you would end up with drippings of copper and tin possibly separating or combining to form bronze. And these materials, depending on the ratios, by accident, would be something that could be worked cold or hot and become something useful. Copper can also be contaminated with arsenic naturally at just the right ratio, and it just effectively self-refines from melted raw ore that goes through a process by accident in the atmosphere at this point. There's still oxygen and other elements involved, and also the carbon at the bottom of a fire pit from charcoal, to a silverish arsenical bronze. And 4200 BC, that is also when that happened. Tin-contaminated copper ore and arsenic-contaminated ore would form tin bronze or arsenic bronze. Any wonder why copper and bronze and eventually brasses occurred? Now, it should be pointed out, if you're already aware of this, some of you are, brass is done by adding zinc. zinc ends up vaporizing and sublimating out of materials and forming a layer on the inside of, let's say, a chimney or inside of a furnace or a kiln. And when you retrieve it, it comes out of this weird material that you can very readily bond with other things. Also makes you really sick if you're exposed to it. If you're not aware of this, Otzi the Iceman, a person who was dug up after being found in the Alps, had arsenic-based bronze, or arsenic and copper mixed metal, that was done by happenstance finding a vein of copper ore that contained just the right materials. And yes, there are examples that contain tin, arsenic, and copper mix, as well as mixing with other elements, including a really weird variety of things where people thought, wow, they were brilliant, they did all these combinations, and it's like, no, they just tried melting everything they could out of it and ended up, getting it dripping out of the rock after it was heating this metal out of it, and just the right conditions, and ending up having it formed really useful items. Once they figured out how to do that, that area became very valuable because you could make very useful products. Because if you're not aware of this, copper can be formed by pouring it into a mold, and then after you get it out of the mold, put it into another mold, a toughening mold, and hit with a hammer, and it will harden the outer layer of it to very close to what you might want to call tool grade metal, like tool grade copper. And you end up with an axe blade that will actually hold an edge and do a decent job. People have done these experiments enough that we now know that's exactly what happened. You'd be getting the edge to bend over a little bit. Okay, well, you'd bang it to straighten it out, and by doing that, you'd work harden it. And it would end up being a lot tougher. It shocks the crystalline structure and causes it to form a grain structure that's a lot tougher. Okay, we're going to do an example of a metal ore of some kind and charcoal being used to compound, and an example of it. This is an example from a website that does this as a chemistry class for students in either high school or college. I can't tell which. 20 grams of dry feed corn to act as a kind of charcoal during the following process. This is poured over the top of 6 grams of washing soda ash or sodium carbonate. This acts as a flux over the top of the next materials. 10 grams of copper carbonate, oxide, doesn't matter which type, roasted mix, where you've already heated it up to cause a reaction to get rid of some of the reactants. And this is mixed with and or on top of 2 grams of tin oxide that has been roasted over charcoal that is also sealed inside of a clay funnel-shaped crucible. This is a thin layer of charcoal acting as a filter and acting as a release agent, like buttering a pan before you make a cake. The crucible has a vent poked in the top of it after it's been sealed so that gases can escape and produce a pressure level that stays up but doesn't cause it to burst. And it's produced then this produces a reducing atmosphere to make a silverish high tin bronze. All these materials and tools are the same as used for making and then glazing pottery. And many pottery glaze experiments would involve ground up material that would be put onto your pottery after you let it heat up and dry in a normal low temperature fire before you would actually fire it in a kiln. And these temperatures were sufficiently high enough that they would cause almost anything to melt over the surface. Suppose for a moment that you wanted to do this in a video game. There's a lot more steps to it, and it seems like it's extra steps, but then again, it's a lot better than just saying you combine copper or, in the case of rust, metal ore, a mixture of lots of different elements, with just carbon in a furnace. So that's about it for the video. I just wanted to bring up the idea of game mechanics versus reality for, in this case, the example of melting or smelting metals or other materials. And that's about it. By the way, the process for sulfur release is very similar to what I was talking about with zinc, where you basically turn it into something that kind of distills on the inside of the chimney. If you want to leave comments, good. If you don't, that's fine too. Lots of links in the description. Hope this has been useful for people looking this sort of thing up, wondering how how this might work, and this is the starting point, not the end point. Thanks for watching. Have a good day. Good luck with that.